Hi, my name is Łukasz Orłowski, and I am a co-founder and CTO of Archanan, a startup that I co-founded in Singapore. And today I would like to talk about how can we leverage large-scale system emulation in the cloud for development workflows and what that offers that our classical approach does not. Okay, there we go. I want to open with a statement that is very, very close to all of us. That is, one size does not fit them all. As we all know, every supercomputer is different. Those differences are exhibited by differences in CPU architectures. They're exhibited in differences in interconnect fabric, in interconnect topologies, in accelerators that we use there, etc. This essentially means that whenever we have a computational software package running on one particular supercomputer, in order for that very package to run on another supercomputer, we need to port it, which means there is going to be a significant development effort involved. And these development efforts are significantly hindered by the practices that haven't really changed that much since the 70s. So when we're developing for a large-scale system like a supercomputer, naturally we would want to make sure that our software run on that very architecture. And we face a first roadblock over here. We cannot use a supercomputer or significant part of that very supercomputer for development purposes. And the reason for that is that supercomputers easily cost of the order of tens of thousands of dollars per day to run. On top of all that, we face hardware availability limitations because those systems are used by multiple users simultaneously. So typically, the practice has it that 10% of a supercomputer is commissioned to development workloads. And basically, my previous point still remains. There are multiple people using those 10%, so we resolve to using debug queues. And we submit our software into the debug queue and wait God knows how long up until the resources are available. Then our software runs on that, and then we get an answer whether it works properly or are there any flaws in it. This is pretty much very similar to using punch cards back in the 70s when we would just, populate a punch card, mail it in, wait for about a week, and then get the punch card back with, like some holes circled up, which basically meant, where we have messed up in our development. It is surprising how little has changed since the 70s. Well, what computational scientists all around the world resolve to do instead, they typically try to develop their software on their workstations or desktop machines. But again, I want to circle back to the original argument that I started with. So, desktop workstation, the desktop machines or workstations are intrinsically different than the target supercomputers that we write for. And I got to give an example. Let's say we are writing for an Intel platform. Our workstation would typically have two sockets interconnect with QPI, Quick Path Interconnect. Then when we want to populate those sockets using Intel, we would probably end up, if we use the latest, greatest offering, we would end up with something of the order of 48 cores per socket. Combined together, that gives us 96 cores. To make math simple, I'm just going to round it up to 100. And now the challenge is we are writing our software to run on tens of thousands of cores, okay? We're talking about 2 orders magnitude difference over here. And nobody who is sane, when put at the gunpoint and asked, will the software that you wrote on your laptop is going to run a supercomputer on the first trial will say yes, because it won't. 9 out of 10 cases, that software doesn't really run on a supercomputer. Then, even if we develop our software on a workstation, we still need to submit it to the debug queue, and then again we gotta wait to see whether our run is successful or not. On top of all that, one other very, very limiting factor is a requirement for affiliation with certain computational institutions. Not everybody right off the street can get access to a supercomputer for development purposes. Okay, so I would like us to consider where cloud could help with those obstacles that I've just listed out right now. And turns out there's quite a couple of things to consider. First and foremost, clouds are generally accessible to everybody worldwide, all around the world. They require no affiliation. Furthermore, typically public cloud providers have abundance of data centers located all around the globe. So we don't need to be physically close to the target supercomputer that we're developing for. Now, one other very important thing with clouds is that cloud transforms capital expenditure to operational expenditure, which essentially means that even if we wanted to commit to developing a solution for large-scale software development, we don't really need to make an expensive commitment in terms of acquiring resources to run our development workflows. Instead, we just pay as we go, and we pay only for what we need. Now, on top of all that, I'd like to add that cloud compute resources are virtually unlimited. And I want to say virtually because naturally, there is going to be a cap somewhere. But we can just continually add the resources that we need. And basically, we can scale out to the size of the system that we actually want to target. Now, on top of all that, clouds leverage economies of scale, which further reduces the cost. So if we look at all the presented arguments over here, clouds are an ideal environment for short at-scale development runs by everybody in the world, regardless whether they have any institutional affiliation or not. So the good news is that all the essential components are available in the cloud. And by the essential components, the essential system components, and by the essential components, I mean compute, memory, network, and storage. And let's explore that in a little bit more detail right now. So when we look at compute, clouds offer abundance of different types of instances that are hosted on different processor architectures. Contemporary public clouds, the leaders in the market, offer Intel architectures, offer AMD EPYC, offer ARMs, offer Power architecture, pretty much everything that most of the supercomputers to date leverage. Then on top of all that, we have instances that offer accelerators, such as GPUs or FPGAs. Now, memory, we have instances with large memory, which are meant for memory intensive computations. We also have memory optimized instances, which basically decrease the latency whenever we reach our memory pretty frequently. And those instances are particularly important in, for instance, genomic workloads, right? Now, network is extremely important. Network is extremely important, and a lot of people tend to neglect it. Contemporary clouds offer Ethernet fabric. They offer InfiniBand fabric, but additionally, they offer software-defined networking capabilities as well as network function virtualization capabilities. This effectively means that we can go pretty wild as to type of the network architecture that we want to span out there. Last but not the least is storage. Storage also is extremely important. There's a lot of different types of workloads that basically use frequent checkpointing, like for instance genomics, and clouds offer state-of-the-art object storage, network attached storage, and high performance block storage, which again allows us to architect our virtual system the way that we architect our virtual system for the purpose of the software that we're running. But there's a lot more. There are also value-added services that clouds offer, such as advanced monitoring, be it in or out of instance, real-time log analytics, real-time stream data analytics, encryption of data at rest and in transit, etc., etc., etc. The environment is there, but unfortunately, the software tools for high-performance computing development in the cloud isn't. And if we look at the prevalent trends in high performance in HPC software tools, most vendors focus on over provisioning and capability bursts, which is a great solution. I mean, whenever we run out of capabilities on our on-prem system, we delegate the excess workload to the cloud, right? But that does not help us really with development workloads. Furthermore, the core development tools, such as debuggers, are meant for the classical 10% development and debug queue scenario, right? So if we wanted to deploy this kind of solutions in the cloud where we can scale out as far as we please, this is going to amount to a pretty hefty amount of money, making it prohibitively expensive to use those solutions. Then on top of all that, as we all know, the key to Linux performance lies in process scheduling. And again, there are no process affinity management solutions readily available for the cloud, as is the case for physical supercomputers. We don't really have profilers that are built for cloud workloads, cloud development workloads. We don't have memory heat analysis tools, etc., etc., etc. Well, not all hope is lost, though. So, I'm sorry. There we go. At Archanan, we took all those considerations into account, building DevCloud, which is I would say, one-stop shop for large-scale computational software development. Archanan DevCloud is an IDE, integrated development environment, available over the browser, which is backed by a powerful supercomputer emulation engine, which emulates our target systems with respect to the 4 dimensions, so to say, that I mentioned before. That is compute, memory, network, and storage. On top of all that, we offer, Archanan DevCloud offers one-to-one software stack replication, leveraging containers, which basically makes us feel as if we were operating on the physical target supercomputer system. One very important feature over here is that we do not have debug queues any longer over here. Think of it this way. Think about it as if every developer that uses DevCloud has their own virtual system replica for their use for development workloads. So we do not need to wait for our software to come back with the results. And on top of all that, we leverage residual cycles, which come at the fraction of the cost of typical on-demand offerings. On top of all that, at Archanan, we built proprietary in-house tools that are tailor-made for cloud workloads. So basically, we cater for scale-out capabilities of the cloud at no extra cost. Doesn't matter if you're running your workload on 50 nodes or 50,000 nodes. The price range is the price tag on it is exactly the same. And finally, since we do not any longer leverage on the 10% development for the system and the debug queue scenario. We get to use the entire virtual development system for our development endeavors, which effectively boosts our productivity 10%. Now, the best part of it is that comes at a fraction of the cost, roughly 10% of the cost that would be involved while developing at the 10% of a physical supercomputer over here. My name is Łukasz Orłowski, co-founder and CTO of Archanan, and I develop at scale. Thank you very much, and I would like to welcome any questions right now.
First question while the others are typing. Could you please elaborate on emulation part? How do you emulate the various CPU architectures and networks and topologies?
Absolutely. Okay, so this is going to be a two-layer question. When it comes to CPU architecture emulation, what we do is whenever available, we leverage the architectures that the clouds offer, right? The ones that I listed. However, there might be more esoteric, so to say, architectures, like for instance, Shenwei architecture, which is national architecture used in China. Now, when it comes to this, we develop our own instruction-accurate emulators, that leverage on QEMU software emulator. Now, developing those emulators, this is a very, very complicated process because it requires us to go really deep into the specifics of every single architecture in question. Now, getting back to the second part of your question, when we talk about the network emulation, well, there is a couple of ways we can go around that, and that essentially boils down to what kind of fabric we want to use, whether that is Ethernet or whether that's InfiniBand, right? As we all know, Ethernet doesn't really like cycles in their topologies. That's why we resort to using converged Ethernet that combats that in a way. InfiniBand does not really have that sort of limitation. So InfiniBand essentially, I want to take a step back over here. What we do over here is basically we span our network, manually deploying. I mean, I don't want to say manually, but deploying different number of virtual network interfaces or virtual fabric interfaces, and basically this way we get to control who talks to whom. Then, on top of all that, if we need some additional network features, that's when SDN comes in, and that basically allows us to simulate scenarios in which, for instance, we draw packages with respect to a certain probabilistic distribution, or basically we can emulate faulty cables, etc., etc., etc. See how the system is able to deal with how our software is able to deal with such faults on such system. Does that answer your question?
Yes, thank you. So, do we have any other question? Looks. Can you see? I can't see anyone typing. So.
Yeah. I don't see anybody in the chat.
So if people are interested in further details, please contact Łukasz directly. And
absolutely, please do not hesitate to reach out.
There is something called there is a question from Anna. Which
yes, which public? That is an excellent question. Currently, we're backing our solution off of Amazon Web Services, AWS. However, we plan. We already have that in the roadmap. We're gonna be porting our offering to Microsoft Azure. We're gonna be porting our offering to Google Cloud Platform, IBM platform, etc. The reason for that is that at the institutional level, a lot of computational centers are forced, whenever they resort to using cloud offerings, they are forced to use particular cloud vendor. Like for instance, in Poland, I know that educational institutions have deals signed with Microsoft, and they have to use Azure. Now, our plan over here is to provide the exact same user experience regardless of which cloud provider you use. And with this, you conform to the you conform to the mandates that your center might have imposed from above.